to make to develop the oneAPI so that scientists can apply the tools for their research and the productivity. So the agenda of today is we are going to level up from the previous talk to talk about the OpenMP parallel programming model that is very useful in getting the performance and also the productivity on modern platform, which is highly hierarchical and also heterogeneous. So I will mention some highlights of the OpenMP to make you aware about the opportunity you have in using the OpenMP for your application development and the science studies you are carrying on. One particular aspect of OpenMP will be the focus of the rest of the talk, namely the enhanced OpenMP composability in oneAPI. So OpenMP is not the tool for everything. It's not going to work very well on multi-nodes, although there are attempts for it. It's not going to be the best speed of light programming model that utilize the AMX or the sister array of the PVC. However, it provides the basic tools and the two-number tools for you to get the best performance you need to enhance your productivity. And as I have, if the time permits, I'd like to go over exciting sciences that are enabled by OpenMP. And yeah, we'll close with at the end. So let's think about the kind of system we have today. So Aurora Exascale supercomputer is just out for the production, and many projects, something like 50, 30 projects are running their science project on this system. And one of the key feature is that it's very hierarchical and it is heterogeneous. There is no single core that goes all the way from one core to millions of the nodes, as happened with the Blue Zinc system about 5 or 10 years ago, depending upon how you count it. So here is the view from the top, the entire system, Exascale system, which composed of the Dragon network that has also the groups of processors to maximize the throughput and latency and the flexible and provide the flexible tools to manage a wide range of the workload. And if we look at the individual node, this is what the Aurora node looks like, or it's a schematic view of it. It has the CPU. In this case, it's a Sapphire Rapid CPU, 2 sockets, and it is connected to 6 GPUs that are also interconnected by or by the fast link X-link. And if we go look into the socket itself, it's also very complicated. It has the chiplet-based architecture, so the SPR is going to be show up as 4 quadrants, or if your computing center decide to run on quad, then you will have a single NUMAS memory domain on the socket. And we have also HBM, high bandwidth on CPUs, and then DDR. So what do we do with this complicated system? And what are the tools what kind of tools we have? I would like to emphasize that OpenMP is one of the tools that can glue many different levels of hierarchies and complexity and make you more productive programmers to use the machine. So the only thing I will ask you to ask yourself about what to do on this heterogeneous system will be, can my problem fit to a fast memory? And the fast memory will be up to you and your problem you have to solve. It could be the whole socket, or it could be a core. And depending upon the problem you want to do and the kind of preference for your programming model, you will be able to program. And OpenMP is really the standard. Sorry about it. Standard of way programming on the shared parallel node. So, so what is OpenMP? I'm very confident that you are very familiar about the programming model and you have been using it in many contexts. But it's good to remind ourselves what it is, what the goals of the OpenMP standard is. It is the tool that is portable and scalable for developing parallel applications, and it is supported on diverse hardwares and by multiple compilers, and then you can run the same code from desktop, laptop including, to the supercomputers. The key features of the OpenMP are, unlike many other API-based library solutions, is that it is a directive-based parallelism, as you can see on the right, that it is the normal C code you will have, and then you are telling the compiler of your intention, how you want to execute the parallelism, and also where you want to run the computations. In this case, you will use the device offload to be able to utilize your accelerators. So it is a shared memory model. The only limitation of the scope of your shared memory domain will be operating system. If your operating system presents a single addressable memory which contains 2 sockets and 6 GPUs, you can use it. But if you find that to be inefficient, then you will define the domain accordingly. And it offers the task and loop parallelism. So very often people ask, what should I do? Should I use OpenMP and Seeker? The basic answer will be, are you a loop person or kernel person? If you think better in the loop, then go ahead and then use OpenMP. Since the OpenMP standard 4.5, it offers really many features to make the device offloading very easy. And also it provides the controllable parameters, not only being able to do it easily, and it also it gives a lot of tools so that you can tune your performance. And the lastly, but most importantly, is a portable programming model on any CPUs and also the range of the GPUs. So here I summarized the key features of the OpenMP spec. I mean, it's going to be impossible for me to go over, but it is very expensive and extensive the specs. And please go ahead and look into what they offer and find out how you can use it. So the title of each release is very interesting. So version 5 says it's a major leap forward because it really added a lot of new features that was not possible before. And that the main, including the device offloading, as we mentioned several times. And also it offers very many interesting ways of the transforming loops you are very familiar with, and then you can also add the concurrency with a very straightforward way. And the version 6, which was released last November at Supercomputing 24, is really for about easier programming. So you took care of the portability part and performance part. Now the standard community is trying to make the programming easy so that you can improve your productivity. So and some key features include really support for parallelization of the latest standard programming models, C and C++, virtually. And then also the standard team improved the interoperability of OpenMP with the native kernel programming model for its GPUs. And this is the list of the supported features that are in oneAPI today, or in fact, it was a little bit outdated because the slide come from the supercomputing last November. So, please have a look at it and let's see if anything is missing for your scientific investigation. Let the standard committee know so that they can enhance the OpenMP standards to meet your need. And one particular feature I will focus on for the rest of the talk is the enhanced OpenMP security PC++ composability and why it matters and how it is going to be used for your science investigation. So we are very familiar with the fact that OpenMP works seamlessly with the existing distributed parallel programming model MPI. So MPI plus X being OpenMP was a de facto for a long time. In fact, Sanjeev gave this history talk, and I can see how QM spec has evolved from 2005 when OpenMP was just really established as the main programming model, and then how it really got improved to support a lot of difficult tests better. So MPI plus OpenMP host threading, I consider that to be just the basics. So I'm not going to talk about much, but now let's think about the heterogeneous node we have that has a lot of cores, many multiple sockets, and sometimes different NUMA domains because the memory architecture is getting more complicated. And depending upon whom you talk to, it could be a chiplet or it could be a core or socket. So in that case, we will be using OpenMP and the performance library like MKL to get the best performance. Now, with the introduction of a GPU or accelerators, what options we have? There are many options, and we know about the seeker and the cooldown heap, and then also the performance library that are developed based on the native kernel programming model. So in this era, OpenMP offload capability can interoperate with existing native programming models so that we can leverage the best performance and also the productivity tools we have. So depending upon the problem you have, it could be just using a half of your NUMA node with the GPU, or it could be two, or it could be the entire circuit. All those things are possible with the OpenMP offload, and then all you have to do is just putting them together. And with the same capability, now you can extend your code to use collective libraries or even Python and the AI frameworks, and then really extend your work beyond the traditional HPC applications. So how is being implemented in oneAPI and how you would want to use it? So one example will be you have OpenMP offload code and you want to use the performance library like in DGEM in MKL, but you want to perform the gem operation on GPU. The answer is very simple. Using the interoperable method, using the dispatch method, all you have to tell the compilers that where the data should go to and where to compute or what computation you want to carry on. So this is a simple example showing what you used to do on CPU and what you can do today on GPU. The bottom is the C example, so slightly modified to give you the flavor of what kind of thing you can do. Now you can create the array on a specific device, and then you can perform the particular data computations on the device identified as a DRAM. So you can easily imagine this entire computation is embedded in the loop, which the host execution, host parallelism can easily parallelize on multiple GPUs. So this is a basic picture you can use today, and you are actually using it without really thinking about it. Going further, so we can imagine putting OpenMP and SQL together, because at the end, MCAT is written in SQL, and the SQL API is the native mode. How do we use it? The answer is very simple because OpenMP standard offers interoperable standards so that it can manage the resources and make the resources available to OpenMP code so that you can do different things. So this is still non-zero effort because we have to talk to SQL somehow. So it will be a universal initialization step that create the device context and also the queue with the SQL. And once you create the SQL queue, then using it will be straightforward. You could easily use the allocations from SQL and then you can move the data, and you can execute the kernel. And I happen to have a very complicated code I have developed over the years using OpenMP. Then we do the OpenMP and kernels or the computation, and we complete with the DGEM. So this is a very cute toy example, but you get the drift and how you are going to be able to use or compose a SQL with the OpenMP and the performance library like MKL. And in this example, I even put the event handling so that the first two steps in SQL will happen asynchronously to the OpenMP target, and then all those things come together and to execute it, to complete the task. So that's all possible with OpenMP. And so this is sort of how the OpenMP interop is being used in QMC pack, and in fact, QMC pack with the great modernization at the funded by the OECP project, now they can really put all these things together and select the best configuration they can use to maximize the performance, and then use them for their studying. So I'd like to give sufficient time for you to conclude. So so there are a lot of data we can go over, but bottom line is you get this acceleration with the standard programming that is portable on multiple hardware, multiple GPUs including. So so OpenMP interoperability is everywhere. In fact, it is really the core of all the OpenMP and MKL applications. The list is quite long. And then it also really opens up utilizing SQL libraries or ecosystem with a very minimal change in applications or the libraries. And now moving forward, this is also very much of the core connectors that makes the AI HPC integration easier. One example is the Tinker HP application that already start using it. And I would argue that any programming model which recognize C and C+ binding is the option. So, however, it doesn't free you from now working hard to optimize it. So do remember that. So since I don't have enough time, so I included many exciting work that is being done with OpenMP. So have a look at them and let us know more, and then also that we can work together to make it better. So yeah, take it over.
Thank you, Jeongnim. So basically through the ECP project and also the bring up of the Aurora machine, we worked on QMC pack to make it portable across all the DOE exascale computing machines, and also non-exascale or the previous petascale machines. So the work, we actually heavily leverage the software technology OpenMP. Most of the kernels, majority of the left QMC pack kernels are now written by OpenMP, plus a bit of minor kernels that used to connect the library cores. We do heavily rely on vendor optimized linear algebra libraries. So the advantage of OpenMP is clear. For actually a lot of kernels, even they are performance critical, we found there's not much difference, I would say, in performance compared to writing them in vendor native models, and ends up writing them in OpenMP save us a lot of time. And for performance non-critical kernels, you know that when doing GPU programming, you just don't want frequent data movement. So you write some glue kernels just to smooth out and bypass data transfer. So these things can also be easily written by OpenMP in our experience. So we end up a very portable code. And through years of effort, we made the code kind of running very well across all the machines, at least in the DOE land. On the right side, you've seen the slides I provide. So the blue, the NVIDIA A100 GPUs on Polaris at ALCF, and the red is for Frontier and blue is for Aurora. So if you actually calculate the raw flops of those hardware, you find it's expected as the increasing performance as going from green to red to blue is expected, but nothing is granted. We actually have to make effort to get every bit of the software cracked. And so far, I would say we are happy with all these platforms allowing QMC Pack to kind of unleash all their compute power for our science needs. So yeah, on the left side, Jeongnim highlight actually we made effort. So you know that even with OpenMP, you can write very bad codes, non-performing at all, or in the GPU land, you end up potentially 10 times slower code. So you have to actually get all the allocations, spectrization, data movement, all those things right. And I found once you understand the GPU programming, as the sound chief said, underlying things are the same, rather you're using OpenMP or native languages. As long as you get them right, actually you can get most performance out of it. I would say we were lucky, but on the other hand, also with the help with all the vendors like Intel providing sufficient software technology to enable all the bits or the computation inside QMC Pack, we end up have a very successful story for the code in both performance and portability. So that's I'd like to add. Yeah.
Thank you. So it is performance portable and productive tool. So please go ahead and then explore and do in how it can help you. Thank you.
Sorry, I was mute. Thank you for your great presentation. It's a time for questions. We have 5 minutes of window before we go for lunch. Are there any questions from the attendees? I think they all feel hungry.
Yeah, it has been a long day. So yes, so here are some resources you can use, and feel free to contact me if you need if you have any questions or requests and suggestions.
Sure. I don't see any questions. Ravi has raised the hand. Ravi, give me a second. Just upgrade you. Yeah, Ravi, feel free to ask your question.
Okay. So can you elaborate on the combination of MPI and OpenMP? What configurations did you use?
Depends on you mean this plot or the previous one. So typically we will be using one MPI per device and as many threads as performance improves. So the key thing is to maximize the throughput, and the best throughput we have found is to use one MPI rank per accelerator GPUs for any platform as far as I know. And then depending upon the CPUs you have and also GPUs you have, you will choose any number of threads that maximize the throughput. So in this case, on Aurora, typically we found the 8 threads or 8 concurrent in order queue is sufficient to drive. So of course that depends on the problem. So up to 6,000 electrons, we do see that is the optimal configuration.